The following work is presented: evaluation of imputation techniques using reanalysis data for meteorological variables in northern Chile. The study is conducted in northern Chile, an extremely arid desert region, where it is difficult to carry out studies on extremes and climate change due to quality issues in meteorological stations records, which appear as incomplete time series. This situation prevents imputation techniques from using data from nearby meteorological stations, as these also present temporal gaps. The climatic characteristics of the study area and the behavior of imputation techniques when using another source of meteorological data, such as reanalysis data, instead of neighboring meteorological stations remains unknown. The contribution and proposed solution of this work is to evaluate 6 different techniques for imputing meteorological time series in northern Chile using reanalysis data. At the same time, to assess the reanalysis data from the CFSR and CFSv2 models as an integrated and alternative source of information to neighboring meteorological stations. Finally, the study reveals the behavior of the imputation techniques and the usefulness of the reanalysis data for imputing meteorological data in the context of the extreme desert climate of northern Chile. A total of 638 meteorological stations were collected, from which records of the main variables were obtained: precipitation, average, minimum, and maximum temperature. The data were processed and cleaned based on different criteria, including geographic analysis, time windows with the greatest amount of data, and correlation analysis. From this, 4 groups of meteorological stations were created for each variable, and the corresponding reanalysis data were obtained according to their coordinates. 6 different techniques are used which employ the reanalysis data as input to create the new value. One of these techniques, direct imputation, simply replaces the missing data with the reanalysis data. 2 types of experiments were carried out, one with continuous temporal gaps and another with random temporal gaps. For each meteorological variable, these 2 types of experiments were applied. Additionally, each imputation technique was analyzed in scenarios containing between 1 and 15 temporal gaps. Here, an example can be seen comparing the value imputed by a technique, yellow line, with the actual value, blue line. This section explains some examples of the results obtained. To evaluate the effectiveness of the techniques and the reanalysis data, residual errors are analyzed for each type of experiment and scenario by meteorological variable, allowing observation of how much the techniques deviate when imputing data. For the case of mean temperature, it can be observed that the WKNNI and KNNI techniques exhibit the lowest residual errors across the different experiments with both continuous and random temporal gaps. For the case of precipitation, the IDW technique shows the lowest residual error, standing out in scenarios with random temporal gaps. The CFSR and CFSv2 models can become a viable source of information for imputing data in meteorological variables in northern Chile. For average temperature, the WKNNI technique has proven to be the most suitable in both groups, while RN has shown the worst performance. For precipitation, the IDW technique has turned out to be the most effective regardless of the type of temporal gaps, random or continuous. WKNNI and HOTTECH have shown good results in various temperature contexts. The RN technique has consistently demonstrated inferior performance in all experiments conducted.